evening to all. Today we are joining for a session under the leadership of IEEE CAS Kerala section. Myself, Anandu Kyar, I am a part of technical team member, IEEE CAS Kerala section. On the behalf of IEEE CAS Kerala section, I warmly welcome you all to the starting session of our long series initiative, Circuit Career. We are delighted to begin this journey today with our first session titled Integrated Circuit from Concept to Product. To lead this session, we are honored to have Mr. Rony Thomas. Mr. Rony Thomas is a design verification engineer with over 8 years of experience in the semiconductor industry, driven by a deep passion for semiconductor technology and innovation. He is currently associated with Intel Corporation and possesses strong expertise in VLSI RTL verification hardware description languages. Beyond his technical expertise, he actively shares insights on semiconductor industry, career development, volunteering, and IEEE related opportunities, inspiring students and young professionals alike. With a warm welcome, I invite Mr. Rony Thomas to enlighten us with an engaging section.
Hello, am I audible?
Yes, sir.
Okay, good evening, everyone. Hope, let me first share my screen. Yeah, I hope it is visible to everyone.
Yes, sir. Yes.
All right. So, thank you all for joining and thank you for inviting me. I hope this will be a productive session for all of you. Before we start, I just want to make like few comments. So I'm planning to take this session as a introductory thing to the semiconductor industry, and that too specifically related to integrated circuits or ICs as we call. So this the intention of today's session is just to get you started on this journey. So this is like a very basic beginner level session, and of course some of you might know these things that I'm about to say, some of you might not, but the important thing is you take away the core concepts so that you can go and explore on your own. So once you if you attend this session, my intention is that next time you see something related to the semiconductor industry, like a term, something, at least you will be a little bit familiar with it. And also there in throughout the session there could be multiple things that you might not understand, and because of lack of time we might not be able to explain everything in detail. I'll try my level best, but what I would suggest is those who would like to explore more should definitely take a note of those key terms, and you can go ahead and do a Google search uh, to know more about this. All right. So, oh, okay. Before one more thing, before we start, anybody who doesn't understand Malayalam? Anybody? You can put in the chat also. All right. അപ്പോൾ ഇംഗ്ലീഷിലും മലയാളത്തിലും ഒരുമിച്ച് എടുക്കുന്നതിൽ കുഴപ്പമില്ലല്ലോ അല്ലേ? Okay. Let's start. So already mentioned ചെയ്ത പോലെ my name is Rony. ഞാൻ ഒരു ഡിസൈൻ വെരിഫിക്കേഷൻ എഞ്ചിനീയർ ആയിട്ട് വർക്ക് ചെയ്യാണ്. And also I've been an IEEE volunteer for the last 13 years. I don't want to get more into this. So yes, before we start, ഞാൻ already പറഞ്ഞ കാര്യങ്ങൾ, but little bit about the semiconductor industry, right? So industry, ഈ ഒരു ഇൻഡസ്ട്രി എന്ന് പറയുന്നത് വളരെ വാസ്റ്റ് ആയിട്ടുള്ള ഒരു ഇൻഡസ്ട്രിയാണ്. So everything from your basic LEDs to the most complex compute chips, everything comes under this VLSI അല്ലെങ്കിൽ semiconductor industry. So അതുകൊണ്ട് തന്നെ we cannot cover all of those here. So we'll be focusing mainly on the thing that we call integrated circuit അല്ലെങ്കിൽ നമ്മുടെ ഭാഷയിൽ chips എന്ന് പറയുന്ന ആ ഒരു ടെക്നോളജിയെ പറ്റിയായിരിക്കും നമ്മൾ ഇന്ന് സംസാരിക്കാൻ പോകുന്നു. And as I already mentioned, this is just a high level overview so that you can start to explain on your own. All right. Coming to integrated circuits. Okay, before I get to that, if you have any questions, any doubts, or if you want me to explain anything once more, please unmute yourself and you can ask your questions or doubts. Or if you can't speak, then please put it in the chat. So volunteers, അതൊന്ന് chat ഒന്ന് monitor ചെയ്തോണം. I might miss when I'm presenting. I might miss to see the chats. So volunteers, please let me know. എന്തെങ്കിലും questions chatൽ വന്നാൽ okay. Yeah, sure, ma'am. Yeah, if there are any questions, please put it in your chat. And volunteers, please notify me if somebody has any questions there. All right. I hope we are all good. Let's start. So, integrated circuits. I'm pretty sure all of you would have seen a chip like this, at some point in your life. Anybody who hasn't? Maybe in some device, some kind of electronic device, something. You would have seen this, right? Yes? Can I get a thumbs up? All right. Yes, I see some. All right. So, yeah, this is what we call as integrated circuits, or commonly we call it as chip. It's a microchip, electronic chip, etc., etc. So this is basically, these are the inventions which is running the digital world right now. Everything from our mobile phones to a simple toy, our wearable devices, to the most powerful computers, the spacecraft which goes to the moon. Everything utilizes some form of chips like this. So here on the screen, you can see two different types of chips. And these two chips are like the two most extremes, almost like the two extremes of this IC product, you can say. Anybody know what is the chip on the left side? What is this one? Anybody has any idea?
This is transistor, right?
Come again?
Transistor.
It's not a transistor, but I can understand the confusion. Yeah, it's not a
It,
more. All right. Yes, Niranjan told the correct answer. It's a voltage regulator. It looks like a transistor, I know, but the name of it should help you identify. This is a 7805 voltage regulator. So basically, the point of this voltage regulator, it's a very simple device. Its only purpose is if you give a varying kind of a voltage within a range to the input pins of this IC, it will hold the output voltage steady at 5 volt. That is basically the purpose of this IC. This is there in almost all kind of electronics in different shapes and sizes. This looks like a MOSFET or a transistor. I can understand that. But yeah, this is like one of the simplest ICs that IC design that you can see. The reason why I put these two together is to show you the absolute scale of this integrated circuits. So if you look at this voltage regulator, you can see it contains almost like 20 transistors. But if you look on the right side, that's an Intel Xeon processor. It's like it's not your typical computer or a laptop or PC processor. It's a server processor, which is basically the CPU which runs all your internet, your AI, everything. So the CPU that runs all the servers of the world. So this is that kind of a CPU, and it has more than 1 billion transistors. So you can see the wide variety, the scale of this. Now, even you have chips with more than trillion transistors inside them. I just kept it. I just took this image a while back. So that is the scale of our integrated circuits. If you look at the IC integrated circuits, you can see in very basic terms, you can convert it into. I mean, you can uh, tell that there are three types of ICs. There is an analog IC, digital IC, and then mixed. Again, I think not very important for us. Yes, coming to the abstraction layers of an IC. So when we say an integrated circuit, when we say that there is this integrated circuit in our hand, it usually comprises of during the manufacturing and design process of this IC, we add these abstraction layers. And what is the reason for this abstraction layer? It's simply the complexity of the IC design. So earlier when this technology was invented, each and every transistor and each and every connection inside this IC could have been drawn by hand. Somebody could design by hand because it had like a handful of transistors, maybe a few resistors. You will see when I show the design of an IC. That was very much possible. But when we talk about like a billion transistors, that level of complexity, nobody can draw it by hand. Nobody can work it nobody can draw that by hand. Manually, it is not possible. So to design ICs of such complexity, we came up with this abstraction layers. Abstraction just means that you are not somebody who is working on one layer of this might not need not be aware of the lower levels, the lower level of abstraction. That's all. So if we look at the lowermost or the base hardware components, it is all like we see in any other circuit. You break open any electronic device in your home, you can see a combination of these types of circuit elements. These are the basic circuit elements. You have transistors, resistors, capacitors, diodes. Then in some things you might have sensors, you might have motors, etc. But everything is like comprised of these basic circuit elements. So an IC also contains these basic circuit elements all connected together in a specific design. That is the lowermost physical layer of the IC. Now, when we combine these things in a specific format, we'll get what we call as circuits. So within an IC, you can say that there are many different circuits which are integrated together. Now, with circuits, we can create gate level modules. Like I think all of you would be familiar with these AND gate, OR gate, NOT gate, etc. So this you will learn in your digital electronics, right? These are some of the basic elements of digital electronics. So this is specific to a digital IC. And so circuits specifically, we group them together to form gates. If it is not a digital, you will directly go from circuit to the module or IP. The module or IP is basically we combine several circuits to form a logical unit. Like in a IC, you will have the input, you will have the output, you will have some kind of processing in between. Like that depends entirely on the IC. And when we have different modules like this all connected together, we get our final product or final IC, which can be like an SoC, which can be a microcontroller, or as I just showed, there is a voltage regulator. I think this might be a little difficult to understand, so let me give you in a more in a example. Let me just explain it using an example. So if you look at this is the top part. That's like a entire IC. This shows the block diagram of an IC. So you can see this port 0, port 2. These are like input output ports. These RAMs, ROMs, those are memory elements. This ALU, this is your main processor, arithmetic logic unit, like that. So you can see different elements, right? So each of these elements you can consider as a module or an IP. So all these modules, they are connected in a specific order. You can see the connections between them. Here it is just shown in a logical way. In a actual physical thing, each of these blue box might contain many different circuits within them. We can even, if it is a digital IC, we can say that inside this there will be gates, and then these gates themselves are made out of a combination of circuit elements. And if you go deeper down, you will finally end up with a circuit comprising of the basic devices that we mentioned, the transistor, resistor, capacitor. So how does it work? Just to take an example, right? So this ALU, this is our module. This is our module or IP. Inside this module, there is a element called a full adder. This is again a basic digital electronics element. If you look at this full adder circuit, a full adder circuit at the gate level is like this. This is one implementation of the full adder circuit. A full adder circuit at the gate level is level implementation of a full adder circuit, because full adder, this is a digital element. You can explain it using gate. So you can see there are 1, 2, 3, 4, 5 gates all connected in a specific fashion. So if you do like that, you will get the functionality of a full adder circuit. Now, if you take like one gate out of this, if you take like one gate, let's take this AND gate. This AND gate is created, the circuit of this AND gate looks something like this. Like this is one implementation of the AND gate. There could be many different implementation based on what kind of design we are going for, but a very basic circuit level implementation of the AND gate is like this. So here we have the power, here we have the ground, we have 3 resistors, we have 2 transistors here connected in this specific fashion. Here we give the input, here we take the output. So it's very simple. It's one of the most simplest electrical circuit that we can think about, electronic circuit that we can think about, right? So this is like the circuit level implementation, and you can see this circuit comprises of the actual physical devices. See, you have these resistors here, 2 transistors, then all this is the power supply, there is the ground, then the input output ports, there are wires which connects these things together. So like this, if you go from top to bottom, you can consider the abstraction layers of an IC. I hope this is a little bit more clear. Why I am presenting this abstraction is just so that you will understand the different layers, how an IC is constructed. Now we are going to look at how this whole thing comes together in the coming steps. But before that, any questions till now? Any questions in this abstraction thing? Okay. All right. So this is again an example. So this is the same 7805 voltage regulator that I showed you. If you look at this 7805 voltage regulator, this is like the block diagram. Each block, you can see there is a starting circuit, there is a reference voltage. Each of this you can consider as a separate IP. All these IPs, when it is connected together, you will get the final chip. So this is again same concept. Another example, like this is like a microcontroller. Each of this block is like an IP. So why we call it as IP is that it is a reusable thing. IP basically means intellectual property. So coming back, if you look at this IP, what you can consider it as it's a reusable thing. So here, I think all of you will be familiar with the IP of USB, right? Your USB connection, your Type C port, that has a hardware. Your chip has a hardware section, a circuit, which understands the signals it is getting through the USB port. Now, that same IP can be used in multiple chips. That same IP, that same design can be integrated into multiple chips. That's why we call it as a module or an IP, because it can be reusable over different chips. Okay. Yeah. Now this is the circuit level implementation of the 7805. So you can see all these colored regions are the different modules that we saw before. We saw that we saw this, right? We saw the starting circuit, the reference voltage, etc. So each of this colored portion is one part of that module, right? Or the circuit of that module. And finally, if you look at the actual physical implementation of that IC, you will look something like this. That we call this as the die of that IC. This is the actual silicon, or this is the actual chip, the picture of the chip. If you strip away the entire protective covering of that chip, you can see something like this. So from this, it is very difficult to understand what is what. Maybe this even I am not able to decode it. Maybe this is like a transistor. This is another transistor. You can see all these different lines going on are all interconnecting wires. So you can consider like that. So yeah, that is basically the abstraction layers of an IC. Now, if you, it's again another example just for people to understand it completely well. If you consider an IC as a building, you can consider that the if you want to build a house or any building for that matter, you need basically three things, right? So in the design and manufacturing process of an IC, the entire lifetime of an IC, you can also consider into three different basic processes. So if you're trying to build a building, you first need a blueprint or a plan. You need to figure out what is the plan, what you're going through. If you're building a house, how many rooms you want, what is the size of each room, uh, where the door is facing, where the windows are, etc. So that is the blueprint, that is the plan. Now, once you have the plan, you can't directly start construction, right? You need to source the materials and the processes that you're going to use. You need to decide, are you going to build it on pillars, are you going to build it from the ground, or are you going to use bricks, are you going to use steel? You have different process, you will have different materials, and once that is done, once that is all set, you will go for your final construction. So similarly, if you think about the process of designing and manufacturing an IC, the first part is the blueprint or the plan or the design. So this is basically where your IC's design comes to picture. So that basically covers three things. So there is a device definition, there is the functional design, and there is the functional validation. Now, what each of this is, we are going to look in the coming slides. But just understand, this is the blueprint stage. This is where the plan comes to picture. Here again, your IC did not, the physical part of the IC did not start. Here it is still at a conceptual stage. It's at a design stage. And then you need to source the process or materials. You need to figure out how you are going to turn this plan into an actual physical thing. So that stage, that intermediate stage is called physical design. I'll explain more when we come to that. And finally, once you do the physical design, based on that physical design and this design, this blueprint and process together comes to form the manufacturing. Finally, you actually manufacture the IC in the fab. Okay, so now we are going to see the design process of a generic chip, a generic IC. So this will involve all these steps that I've already mentioned. So this is kind of like a very simplified design flow of an IC. Before I go deeper into this, any questions till now? Any doubts? Anything that I need to explain again? Okay, nothing. Fine. Let's move on. So this is this you can consider as a very basic design flow of an IC. Now, I have simplified it a lot for your understanding. Each of this box you can shift. You can consider it as a uh, you can have a very lengthy explanation into each of this, but my plan for today is I'll just give you an intro of what each of these things are. So we start with the device definition, functional design, and functional validation. So these three processes are related to, that is equivalent to the blueprint stage of our building. Okay, so first we will see those three things. All right, so device definition. This is like the starting point of our IC. This is where our IC, what our IC is supposed to do, that takes into effect. How we are going to do comes later. This is where we define the what are ICs. Is my IC a voltage regulator? Is my IC an SoC microcontroller, a microprocessor, or a digital signal processor? What is my IC? What is its role? What is the functionality of each of the blocks within that IC? What all blocks should I put in that IC? That this all depends on what our IC is, right? So this involves, first we need to look at the market and we need to look at the customer requirements. What does the customer want? So if you have been noticing, recently all the new phones, they will say that yeah, they have a dedicated AI engine inside their IC, whether it's a Qualcomm processor or a MediaTek processor or even an Apple. They will all boast that okay, I have a dedicated AI engine, a hardware AI engine in the processor. Why do they do that? Because now customers are demanding that. Customers want their phones to be able to do AI things faster. So for that matter, now every company which is designing ICs for phones, they are now adding dedicated AI blocks. Even if you look at even the desktop or laptop process, even they are saying that they have very dedicated uh, blocks for handling AI tasks. Now that is what we mean by the customer requirement. The customers want it. That's a good feature for customers to have. So the companies are putting it. So once we have that, once we decide what is the requirement of our IC, then we need to figure out what all blocks, what are the functional blocks. Then that functionality will be divided into smaller blocks for ease of design. Then we also have to define the constraints of an IC. When I say the constraints of an IC, every IC will have limits to its performance. So for example, if you're talking about a digital IC, your digital IC will have a certain clock speed. So if you look at microprocessors or microcontrollers, they will always have this thing called what is the maximum frequency it can work. Some of it might be 2.5 gigahertz, 3 gigahertz, something like that. So those are like, there are multiple constraints like that. What is the temperature limit? What is the temperature it can sustain? What is the voltage? What is the current? What is the power draw that it is having, etc. There are multiple constraints like this, and it will depend based on what your IC is. So IC which goes into a laptop, that will have a different set of constraints than an IC which is going into a car. The uh, that the IC which is going inside a moving vehicle, that will have a lot more set of constraints than whatever is going inside your phone or your laptop, right? So like that. And then one other thing that the companies have to see is, do we have the feasibility to implement this product? Do we have enough fund? Do we have enough manpower? Do we have enough technical expertise? For a manufacturer, they should see, do we have enough capacity to produce these many chips, right? So all these things come into picture, and all these are considered right at the very start of start an IC. Whenever we plan and start executing on a new IC, all these things must be somewhat clear. It's not necessary that all these things will be 100% fixed without any deviation. It's not like that. But there should be a basic device definition on which your rest of the flow should happen. Of course, during the design process of an IC, some of these device definition decisions might change. That can happen. That depends on market conditions. That depends on technical feasibility. Depends on the cost, etc. Some of these changes can happen, but anyway, at the very beginning of the flow, we define all these things. All these things have to be at least defined to a certain level. Okay, so I hope that point is clear. Any questions before we move to the next one? All right. So once we have the device definition, now we will start on the functional design. So if you have noticed, you can see that there are two types of designs that I have put here. There is a functional design and there is a physical design. Now, why is that? The functional design is like, that's why I showed. Excuse me, any questions? Any questions? Okay. Yeah. So this functional design, as we had seen before, it is like the blueprint stage. This is where the plan, we are only at the planning stage, or we only do the conceptual design. We are not, we have not yet gone into the physical realm, right? This is all in, you can say, in paper, or you can in the current world, this is all in software, all in design, all in our computers. Nothing has been manufactured, nothing has gone physically. So that is the functional design. And physical design is where we turn the functional design into a physically manufacturable level. I think rather than confusing you now, I'll explain it when I reach there. So what happens in functional design? Functional design is basically where we design the circuit which is inside our IC. So if you remember, I showed you the 7805 circuit. I showed you another simple circuit example. So we have to design that particular circuit, which will be inside our IC, which will be the actual functioning part of our IC. So that circuit will be designed based on the based on the device definition that we did. When we did the device definition, we decided that what all things has to be inside our IC. So if it is, let's say, a microcontroller, as we saw before, it should have an input pin, it should have output pins, it should have like an ALU which does all the data processing. So likewise, each and every part of that IC design has to happen here. Now, in our terminology, we call this as RTL design stage. That is specific to a digital IC. We call it as RTL design. And how we do it is, this is again specific to digital. Analog is somewhat similar, but not exactly the same. So we are not like designing circuit at a transistor level. We cannot draw transistor level circuits uh, with the complex ICs of today. As I mentioned, we have billions of transistors, billions of elements inside a single IC. So it's not possible to manually draw those. Even with the help of software, we cannot implement it at a transistor or a device level. So that's why we have come up with tools which help us to define the functionality of an IC through like a programming interface, right? So if you see here, this is a simple example that I did. So this particular language, I think most of you will be familiar with programming languages, right? So this is a particular type of language called HDL languages, hardware descriptive language, HDL. So this is one type of HDL. This particular language is called system Verilog. Similar to this, you have Verilog, you have VHDL, etc. So if you look at it a little bit more closer, this is almost like something like a C++ or a C or any other programming language that you're familiar with, right? We are using human kind of words or human kind of uh, like a language constructs, but we are defining the actual hardware here. We are defining the functionality of the hardware, what my chip, what my design should look like. So here you can see I am giving it like three inputs. then I'm putting an output here, which is here you can see it's a 4-bit output. It's one wire with 4 bits, right? So I am telling my system or this tool. So these tools are called EDA tools. EDA stands for Electronic Design Automation. We have EDA tools where we use these HDL languages to explain to the EDA tool what my IC should be, what is the functionality, what my hardware should work like. So if you see, I'm defining the inputs and outputs, and here I'm giving it like a condition. I'm giving it, I think all of you would be familiar with this if else if cases, right? It's a very basic condition. I'm giving a condition. If this is the case, my hardware should be 0. If this is the case, my hardware should start counting. So it's a very simple design. Now, my EDA tool can take an input like this from me, and then it can convert it into a possible hardware design. So if you see below, this is the hardware level implementation of my program that I gave. This system verilog program, if it has to be put into a hardware, it will look something like this. Again, this is just a block diagram. We are still at the conceptual stage, but this block diagram will be converted into an actual circuit later on, right? So if you look at just this block diagram, you can see I have defined 3 inputs. Here it is showing 3 input pins. Here I have put some logic, and that logic is implemented through this particular circuit. So if you see, this is an adder, this is an adder, right? This is a multiplexer, this is again a multiplexer, this is a D flip-flop. So these are all basic circuit elements, and my EDA tool is intelligent enough to understand what I am trying to do through these programs, and it can convert it into a basic circuit like this. So this is my output. So you see, right? So I don't want to go into the detail of each of these things, but just understand that my EDA tools does this translation to for me. So just like when you do a C program and you do a compile and you get an executable element, just like that, I am here compiling my code, my hardware code, and this is the possible implementation. Again, there could be multiple possible implementations. Like instead of a multiplexer here, it can be there can be a different element here which serves the same purpose, which basically gives the same logic, but this particular EDA tool implemented it like this. So all those are controllable by various options. Now, if we again go back to the abstraction points, right? This is my hardware circuit. Now, here is my adder. My adder's gate level circuit is like this, and inside my adder, my and gate will look like this. So finally, each of these elements, each of this adder, this D flip flop, every element in this circuit diagram finally will be converted into a diagram, into a circuit which comprises of our basic circuit elements. Our basic circuit elements, if you remember, it's like transistors, resistors, capacitors, diodes, then all the interconnecting wires, then power supply. All these things are our basic circuit elements. So each of these modules, each of this module, or you can say this is like one IP, this is another IP. So each of this will be finally available as a circuit in terms of the basic circuit elements, the basic devices that we saw before. So that is how we design complex ICs with billions and billions of transistors. We are not directly connecting transistors like this, but we are basically using these kind of programs, these kind of tools. Again, this I'm specifically talking about digital design. Analog has a different flow, which I don't want to, that is a little bit more complex than this. So anybody who's interested, you should first look at digital design and understand the concepts really well, and then go to analog, because designing analog has a little bit more complexity to it. Okay. Yeah. Functional design is clear to everyone? Any questions? Okay, right. Now we move on to the functional validation. Now, functional validation is basically just testing the functional design with the device definition, right? So, functional validation, you are doing simulation or emulation of the design, the code that you did, right? There are various methodologies we can use here in functional validation. But one thing to note here is we don't have the IC in our hand. We don't have the physical implementation. We are testing the design which we kept, which we created in the functional design stage. So if you look at the simulation, this is an example of simulation. The simulation basically means you are simulating this code, means you are running this code using its mathematical approximations, right? So for example, we know how an adder works. If I give a certain input to an adder, I know how my adder is going to behave. I mean, that is the ideal case. Ideally, I know how my adder is going to behave. When it comes to the actual device, there would be slight variations here and there based on how our IC is designed. That's a different story, but at least from a design point of view, we have an expectation of how an adder works. So based on that, we have other tools called simulators, where we give the code. We give the input code that we designed during the functional design phase, and on top of that code, we will have something called an additional set of code using the same system Verilog called test bench. Now, this is entirely my test bench code to test the functional design that which I showed you before, right? The purpose of this entire piece of code is just to give some inputs to my design and then observe what it is doing. What is it? And we run the simulation for a certain time or a certain number of clock cycles, and then we observe how is it behaving. Now, this entire piece of code, the logic in this code, it's not going to be manufactured. This is not going to be in the final design. This is the only purpose of this code is just to test our functional design. So if once I do the simulation, I can have various tools to analyze it. So this is one of the major tools that we use, which is it's called a waveform. So once I run this simulation, this test bench code on top of my design, I can see how it behaves, how my design behaves. So if you can see, these 1, 2, 3 are my inputs and this is my output. So I can see based on the combination of inputs that I'm giving, based on the specific combination of inputs, I can see that my output is changing. So now we need to ensure that my output is behaving as expected from the device definition. If there is some issue in my design, then we have to again go back to functional design guys and say, hey, there is this problem, there is this bug. So you can see this is like a cyclic relationship. Functional design will have like design version 1.0. Functional validation guys will do their testing, and then they will give their feedback back to the design team. Hey, we found these problems, fix it. Then they will come up with functional design 2.0. So this is like a cyclic process which goes on for a certain amount of time until we iron out all the bugs. We find almost all the bugs. I mean, we cannot say that 100% bugs we will catch, but we try to find all the bugs as much as possible in this functional validation stage itself. Now, the reason for that is if it escapes in this stage and it goes into manufacturing, then sometimes based on the severity of the bug, severity of the defect, our entire IC will be basically useless. So it is very essential that we find all the issues in our design at this stage itself, because at this stage it is easy to correct. But once it is manufactured, once it is physical, you cannot do much about it. There are some techniques that you can do still, but nothing which is there to there is no robust solution for us. This is not like a full circuit where you can change the wire, or you can connect a jumper wire and fix it. That's not the case here. We are talking about nanometer level electronics, right? You cannot simply uh, break one connection and give another. I mean, it is possible to a certain degree, but it's not feasible at a very large scale. So that's why it is said that for every functional design engineer in an organization, there will be at least like 3 or 4 functional validation engineers who are trying to break that design, who are trying to figure out all the bugs. So this functional validation, it is a very important stage in the design process of an IC. So once this is all done and we have the final functional design, then comes the physical design part. Now, if you remember the example that I gave, these 3 things, this was the blueprint stage. So we are still at the conceptual or a design stage only. We don't have anything physical. We have just the circuit design till this point. Now we come to the physical design, where we are basically taking the electronic circuit, and we are trying to convert it into a format which can be manufactured. So here we are choosing what kind of physical devices we are going to use, what kind of AND gates, what kind of OR gates. So there are different possibilities.
Hello.
You can have, yes, any questions?
What are the software used for validation?
Come again.
What are the software we use for validation?
Validation. So there are multiple softwares. So VCS is one of the softwares. VCS is then VCS is from a company called Synopsys. Then Cadence has one tool. I forgot the name. So we have major 3 EDA vendors in the industry. These are the major players. We have Synopsys, we have Cadence, and then we have Siemens or Mentor Graphics. These are the 3 companies which provide all the industrial level tools for us, right? So Synopsys has this tool called VCS, which is both a design and validation tool, which is both a simulator and a design tool. We have VCS and VCS Sim, which we use. Cadence has something similar. I just forgot the name. Then Synopsys has FPGA based solutions, which we can again use. So there is another technique which we use in along with simulation. We also do something called as emulation. Again, I don't have time to explain everything. So if anybody wants to understand more, you can go for FPGA emulation. What it means, you can just search for it. It's pretty self-explanatory if you do a Google search. So likewise for Synopsys, we have emulation platform called Zebu. Then Cadence has a emulation platform called Palladium. So there are multiple tools like this, and of course there are open source tools for doing all these things. But again, I don't remember the names on the top of my head. Okay, that answers your question. Okay, right. So we were looking at physical design, right? So physical design is basically where we take the functional design or the circuit that we created. Now we need to move it into a format which can be manufactured. Still, we are at this stage also, we are not going into the physical realm yet. We are not reached there. That will only come during manufacturing, after manufacturing. But this is the intermediate stage which converts a circuit or a conceptual design into a physical format. I think you will understand more when I show you this. Yeah. So if you see like this, each of this is a separate block. You can consider each of this as a module. So this was all like, if you see this entire thing, this is a CPU block, right? This is a CPU block. Each of these boxes here, these are our input output pins. This is the actual representation of the physical format of our IC. So in real world, our IC will look something like this, right? It will be in a square shape like this. And if you look inside the IC, all these will be the circuit level implementation of our input or output pins. This is the circuit level, this whole region. This is the circuit level implementation of our CPU, right? So if we go zoom in inside this, you can see the various transistors and resistors, capacitors all connected in a specific format based on the circuit that we created. There are millions and millions of transistors in just the small part, so we cannot see it individually, but just understand that if you go and zoom deeper and deeper into this, you can see there will be the actual circuit, actual electrical circuit comprising of all our basic elements interconnected together. Now we have taken that conceptual design. In the concept, we just have a circuit diagram. Now we took that circuit diagram, all the elements in that circuit, and we made it into a physical format. We have arranged it into a physical format. And this design is what our manufacturing is going to use. It is going to look at this design, and inside the chip, at each and every point, it will create the circuit element which is given by this design, this physical design. So let's say that at this point, there is 100 transistors. I don't know if you can see my cursor, right? Let's say at this point, there are 100 transistors connected in a specific fashion. When the chip is manufactured, now our the tools in manufacturing knows that at this point inside our actual chip, it has to manufacture 100 transistors and then connect it in a specific way. So I hope that is clear. This is the intermediate stage, or this is where the conceptual is being converted into physical. It is not yet physical, but it's converted into a physical format. Again, this pictorial representation is just for our understanding. It is just for human eyes to understand. The actual design will be a binary kind of a file. It's a machine readable file that we will not understand. It will be like junk for us. It will be a full list of ones and zeros only, right? So it won't make sense to us. That's why all the tools have, all the physical design tools have ways to represent it in a pictorial format so that we'll understand. Again, this is another way to represent it. So if you see, this is actually the physical design of our 7805 IC, the physical design implementation. So if you see, you can consider these blue things. These are all the different wires that interconnect. These red things, these are all the transistor blocks that you can see. This is like a big heat sink, which is used to eliminate the heat. So all these things. This again, as I mentioned, this is just a pictorial representation for our understanding. The actual file will be a machine readable file, which the machines in the fab will understand. Machines in the manufacturing plant will understand. We won't understand looking at it. Now another stage in this physical design is to create these things called as masks. Now these masks are something which we use to create patterns on our semiconductor material, and it is based on that pattern. That pattern decides what gets manufactured at what point in our IC. Okay, I think I'll explain that more when we come to the manufacturing part. So I hope this much is clear. Any doubts here?
Sir,
Any
would you please, I have one doubt, sir.
Yes,
Hello.
yes, ma'am. Yes, ma'am.
Yeah. Like you have said that the physical design is the intermediate stage, which
Yeah.
convert the concept into physical format. You said that
Yes.
physical format is the machine readable format, and which represents zeros and ones. What that binary information exactly represents? Could you please give some examples, sir? So, wouldn't get into the deep concept.
Okay. So
That binary format, what that binary format represent in the physical design?
okay. So what I
Yeah,
mean by that is
a few
so just
examples, just a few examples. Yeah,
yeah, I got it, ma'am. So
yeah,
just consider that when we manufacture, we start with a basic semiconductor block, which doesn't have any logic, any transistor, any resistor, nothing inside. It's a basic thing. Let's take the example of a silicon chip. So we call these basic blocks as the die, the silicon die. We take a pure silicon die without anything. So it is just pure silicon. Now to have a transistor at any point inside this silicon, you need to dope it with a p region, n region, and another p region. Only then you will have a pnp transistor, right? So where that transistor will be in this physical design, so consider this is our blank silicon die. So this physical design, it will take the conceptual design. So the conceptual design will have how many number of transistors, where is the transistor connected, which transistor is connected to which other transistor. So all this circuit level functional information, the functional design has. Now the physical design tool, it will take that functional design and it will try to arrange those transistors, resistors, capacitors, all those things, and of course the interconnecting wires on our chip. Again, I'm talking about a very basic a single layer kind of a chip. Today the advanced chips are like multi-layer. You have different logic on different layers. I don't want to go into that, but just to understand, right? So there is, let's say that there needs to be a transistor at this point physically, right? This is let's say this is a 2 millimeter into 2 millimeter square. At this particular point inside that square piece of silicon, according to my physical design, there needs to be a transistor. So that information will be translated in a binary format, in a machine readable format. How that format is, I cannot explain now, because that depends entirely on the tool and that depends on the company, because that format is like not like a, there are some standards, but of course based on the different companies like Intel fab, that design language might be slightly different from what TSMC is using. So each fab will have their own design language. So the basic physical, if you say that at this point there is a transistor, then that transistor is connected to, let's say, another transistor here. So then this whole thing has to route. There should be like a trace between them, a wire between them. Usually it is gold wire or copper wire kind of thing, right? So that information will be stored in a machine readable format at the end of physical design. The output of physical design is, let's say there is a particular file. I forgot the file format. It had like let me think. I think it is called GDS. That's like a standard format. So that GDS file, I mean, it's not just one file. There will be multiple layers of file. So that file will have information of which transistor should go, which transistor should be manufactured at which exact point of your IC. So it will have the dimension of your IC, of course, and then which transistor goes where the transistor, this transistor, the base of this transistor should be connected to, let's say, the collector of another transistor. So that kind of routing information and placement information, that's what we had. I think I didn't explain all those steps. So we have these different steps in physical design. We have partitioning, floor planning, placement, routing, etc. I didn't want to go into details, but if anyone wants, can search for more. So through all these steps, we will come to a point where each and every transistor in our design is placed and it is connected to whatever it should be connected. So that is basically physical design. And if you want to know more about the GDS format, you can go. There is a standard GDS format, and there is an open source GDS format which we can look at. But again, I think that is beyond the scope of our current discussion. So I hope, ma'am, it's clear, right?
Exactly, sir. Exactly. Thank you so much, sir.
Okay, thank you.
Yeah.
Yeah. So I think physical design is somewhat clear to everyone. So once we have this physical design, it is this physical design file, this GDS file, which is going into the manufacturing plant. I mean, it's not just the GDS file. You also have to have the mask. You also have to have the materials. Again, going back to the building analogy. So you have these are the blueprints. At the physical design stage, you convert the blueprint into an actual executable format, and then you take all the different materials. You take the semiconductor material, you take the mask, you take all the other chemicals which is used in this process, and then you take it all into manufacturing. And after the manufacturing, you get the actual physical IC. So manufacturing is basically taking the design and converting it into an actual physical IC. Then you need to package that IC, you need to do quality testing on that IC, etc. So all these stages happen during the manufacturing. And the major step in this manufacturing is something called as lithography. So how we can implement like billions and billions of transistors into such a small space is because of this process called as photolithography. Photo is basically it is imprinting patterns at the very basic level. Lithography just means you are imprinting a pattern on another thing. That's the basic idea. Photolithography means you are using light to imprint that pattern. So this shows you some of the steps that silicon wafer, or we call this basic semiconductor material, this pure semiconductor material as a wafer. It's usually round in shape. So that wafer is like a blank slate. On that wafer, we can create transistors, we can create resistors, we can create the interconnects between all these things, etc. Now, how that is done, it's a pretty complex process. Anybody is interested, go and search for semiconductor lithography or simply photolithography. You see there are plenty of YouTube videos which gives you like in-depth knowledge about that. Again, I want to explain all these stuff, all these steps, but because of lack of time, I think we cannot get to that right now. So this one chip, for one chip, it will have to go through multiple steps of lithography, multiple stages of lithography. Then there is all chemical depositions, then washing away that chemical depositions, then there is physical grinding, there is chemical washing away of those what you say photoresist material. It's a pretty complex what you say flow. In fact, it could be one of the most complex manufacturing process ever invented by man. So it is because it requires that level of precision. We are talking about right now the latest things, we are talking about nanometer scale, right? 1 nanometer, 2 nanometer, 0.7 nanometer. At that level, even a speck of dust, if it falls on this wafer, your that entire chip might be unusable. Your transistor may not work. So that's why this process happens in a place called clean room. So that clean room is much more. It is like 1,000 times cleaner than your typical operating theater. That's what they say. So the particles there, the air particles, the dust particles there are very small, right? Anyway, that's a different line of thought. I don't want to go deeper into that. So yeah, just to show the lithography a little bit more, right? So you have a light source, which is usually lasers. Then you have this mask. Remember the mask that we saw during the physical design thing, right? So this mask basically will have a pattern. That pattern, it goes through some lens and it will fall on the semiconductor wafer, the silicon or whatever semiconductor wafer. You can have multiple different what you say the semiconductor materials. You can have silicon, you can have germanium, You can have gallium nitride, etc. That's all different types of semiconductor material. So it will be coated by something called as a photoresist. Photoresist is basically a chemical which reacts to this particular kind of light. So how it happens is when this pattern is illuminated on this wafer, that much part might be solidified and the others can be washed away, or it is the other way. The place where the light falls can be washed away, the other part remains solid. Like it, again, that's all lot of material science, chemical processing, all those happens. So just to give you an understanding, right? You imprint a pattern, and then let's say that you have this pattern created. If you add a particular chemical in that pattern, only where those patterns are, then all those regions you can create to be like a P region. Again, this wafer is pure, consider it as pure silicon. You imprint a pattern on that, and then only where that pattern is there, you can introduce a specific chemical. And based on that specific chemical, it can turn into a P region, it can turn into an N region, or it can turn into, if you are like depositing copper or gold particles there, it can turn into an interconnect, a wire interconnect. So that's how, layer by layer, step by step, our entire circuit will be implemented on a wafer. And if you see, right, there are all these small squares. Each one is a separate chip. You have this large wafer. I guess this will give you a better idea. You have this large wafer of different sizes. Different manufacturing technology uses different size. This is like a 300 millimeter, 300 mm, what you say, diameter silicon wafer, right? You can see each of this square, individual square, is one chip. So once this is manufactured, once this is implemented using this photolithography and all the chemical processes, this will be cut. Each of this will be cut at their edges, and then each of them will be individually packaged. So on this side, this picture, right, you can see like a cross section of our finished chip or die, as we call this. Each of these individual squares is called as a die. So if you see here at the very bottom layer or the innermost layer, you can see the transistors, resistors, etc. Usually it is all these transistors, resistors are in the lowermost layers, like the last 2 or 3 layers. You will have all these things. Then towards the top, you will have all these interconnect regions. So this orange color represents copper interconnects. Again, you can print a pattern and then you can add copper layers, copper ions there. So you can build a layer like this. And then this huge thing, this large thing is the input output ports. So yeah, these things, this is the what I showed, right? So once you have the die, this is that square piece. Each square piece, that is called as the die. And once you have the die, you connect that input output pins like this. I mean, there are multiple ways of packaging. So this whole process called packaging. Then you cover the entire thing in some protective thing, because you cannot expose this die outside, because even if another piece of dust comes and sits on that die, that region might not work as expected. When you're giving an input to the transistor, it may not behave as expected, right? So that's why it is always necessary to package our semiconductor die. And when we do this entire packaging and all, then we get a IC like this. I hope all of you have seen this, right? So that is the manufacturing part. So we have covered almost like the entire things, and now there are like few things left. As you can see, there is this thing called post-silicon validation. Now here we did functional validation on the actual design. Then during physical design also, there is physical validation where you are checking between the functional design and the physical design. Now that we have our IC manufactured, we go for what is called as post-silicon validation, or this is like the real-world testing of our IC. Usually, what happens when we create an IC in the industry, right? We basically do not send the first level of ICs out. We will first have a batch of test chips. We will do all sort of testing on that chip to make sure that we don't have any issue. If we don't find any serious issues, we will then go for mass manufacturing and we will send out those ICs. If we have like some defects, some companies will do a second round of design, like a limited round. It's not like the full process has to continue. So you, when we do post silicon testing, this is an actual physical board where we do post silicon testing. We can see here, this is the slot for our chip. This is the slot where our actual physical chip will be inserted. And you can see all these other components are testing components. So you have RAM slots here, you have other connectivity slots here, all these kind of things. So from there, we actually test. We give the actual voltages, actual currents, actual workloads, right, onto this chip, onto this test chip. We test it in all sort of ways. We stress test it. We test its maximum temperature resistance, how maximum current it can draw, etc. We purposely drive our chip to its breaking point. Right? We will give it extra voltage to see till what point it can sustain. In that process, some chips will be burned, of course, but this is again all parts of testing. So once this post silicon testing also happens, if needed, there will be a small functional revision, and then again validation physical design has to happen, and then we go for mass manufacturing. And it's these mass manufactured chips that we send out to the customer. It can be like a consumer chip, like what we see in our phones or laptops and all, or it can be like an industrial chip which is for industrial customers. You get the point, right? Now, along with this, I have shown like two more things. This is not related to the physical IC, but this is like firmware is basically, it is a it's a special kind of software code which resides inside the memory of your IC. This is also usually done, the basic firmware of an IC, it is usually done by the semiconductor manufacturer itself. So it's not technically a software in the sense that you understand. Like it's not the software update that you receive on your phone, but this is like a very primitive code or a basic code which resides inside your IC. So and that is useful for bring up of that IC, the proper working of that IC. So when you give power to an IC, again, this is only applicable for things like microcontrollers, microprocessors, those kind of complex, very complex functional ICs, right? You don't need a firmware for the 7805 microcontroller to work. That is a pure analog IC. You don't need anything for that to work. You just give the input, it will give you the output, right? But for a complex thing like a microcontroller or a microprocessor, so for the things inside your phone, many functionality of your IC is determined by what firmware is loaded inside your IC. Some ICs you can have firmware patches, like you can reprogram the firmware, but some ICs, once firmware is programmed into the IC's memory, you cannot change it. For the rest of the life of that IC, you cannot alter it. So there are different types. So again, that firmware, so you might be familiar with the term called BIOS or RTOS. These things, these can be like different types of firmware. Again, very complex field. Don't want to confuse you more. Just understand that there is a certain software kind of or a code kind of thing also to the VLSI industry or to this IC industry. So that is also there. Just it's just there for your understanding. So that covers our entire design flow of a generic IC from start to finish, from the planning stage to manufacturing and testing and everything. So any doubts here? Any doubts? All right, so we are almost out of time. So let me just quickly run through a few more, just two more slides I have. So this is for anybody who wants to start a career in this industry. You can, of course, go for placements if you have it in your college, but again, only like top tier colleges usually get direct placements. Another, of course, direct route is you can apply for direct interviews, but again, you need to learn something in for this rather than just directly applying. Another little bit more easier way, I would say, is to look for internships. No, internship, getting an internship is not as difficult as placements, but generally what happens in the semiconductor industry is that they look for long-term internships, like 9 to 12 months or 6 months at least. I don't know the feasibility of that in our current situation, but I personally did a 1 year long internship because my when I was doing my post graduation, my university allowed that. In fact, my university encouraged that. So that's how I got into Intel. I was an intern there, and then I got converted as a full-time employee. Of course, if you want to learn in depth of this, you can go for a post graduation, but always remember, go join a really good institute. You should look at the teaching in that institute, and you should look at whether they have all the necessary tools and all those things necessary, like the software and hardware tools, because this is the unlike regular electronics. VLSI tools are very expensive. Of course, we have open source tools and all, but the commercial tools which companies use, like the Cadence and the Synopsys things that I said, those are really, really expensive. So you need to see, if you're going for a post graduation, you need to see that your institute has access to at least some of these tools so that you can practice on that. And of course, if you're going for post graduation, also look at placements, the possibility of placements, at least internships, right? If your institute offers good internship, at least that much you need to see. Well, because that's again the easiest way that you can get into the industry. Getting into the industry is, I feel, the most difficult part. Once you get in the industry, you can upskill yourself and then you can go to a better company. That is still easier. But getting into the industry as a fresher, that's a little bit tough part. So if you're going for a post graduation, always keep that in mind. And of course, there are specialization courses. Specialization courses are like 6 months or 3 months course, which teaches you a specific part of this design. Like it could be the functional design, it could be physical design, it could be the validation part. It will teach you. They will give you like a crash course on that specific skill. They will teach you. There are a lot of institutes in Kerala, in Bangalore, in Hyderabad. There are a lot of institutes. I am not going to endorse anyone. You do your own research, and you can go if you are interested. Yeah, so these are some of the possibilities where you can start your career. And my advice for anybody looking to join this is always be strong in your fundamentals, because that is what is very important, because it's a very technical intensive field. So you need to be strong in your fundamentals, like digital electronics, analog electronics, maybe the VLSI fundamentals, the gate level fundamentals, etc. You need to know that. Also, try to gain practical knowledge. There are things like chip to startup programs and all happening nowadays. So you can try and gain some practical knowledge. At least I won't say that you have to go and design your own chip and manufacture it. That might be a little bit difficult, but I know people in Kerala who are doing that, right? So in some institutes, they have their own, they are training their students to do that. That is really good. But at least do some design and do some simulations and understand the whole process, right? Then it's very important to understand the industry demands, because this keeps on changing, right? At some points it will be more requirement for designers. At some point it will be more requirement for physical designers. Like that, the industry trends keep changing. So try to understand what the industry is looking for. For that, you need to network with professionals and recruiters, and you can attend conferences, you can attend technical conclaves, etc., to know more about that. And one other thing that I would suggest you guys to do right now when you're studying itself is look at the job portals of these major semiconductor companies. Like for example, Intel. Intel will post, look at the fresher job opportunities. They will say that, okay, we are looking for a fresher design engineer, RTL design engineer. And in the job description, you will usually see what skills they are looking for. So there you will get an idea, okay, I need to have this skill. Or they might say, okay, we are looking for someone with expertise in this particular tool. Then you will understand, okay, maybe I should study that if it is possible. So that is one way to understand what the industry is looking for and how you can upskill yourself so that someday you can come into this VLSI industry. So yeah, that's just my take on it, just my advice. So once again, thank you all for patiently listening to me, and I hope this session was useful. Now we have a few minutes for last round of questions. I know we are out of time.
Hello. Am I audible?
Yeah, tell me. You have a
Sir,
question?
right now I'm doing MSc Electronics. So
MSc,
if I
MSc
do
Electronics.
MSc Electronics and if I do some courses from NILIT or any private institute, so would it work for my professional career?
Yes, so you are specifically talking about VLSI, is it?
Yeah, correct.
Yeah, see, as I mentioned, that it depends on entirely your interest and all. So NEELIT has some good courses. NEELIT has some good courses, but just doing courses alone may not be that useful because that will give you a theoretical knowledge, of course, but doing that course along with some level of practical knowledge, like designing, you know, downloading at least some of these tools will have student versions, or your institute might have some of these tools available. Taking the time to understand that tool, try start with a very small design. Even you
Sir,
can get
sir, my
yeah.
main doubt is that if somehow I curate these skills that are required by the industry, then
Yeah.
is there any discrimination or partiality with MSc Electronics because most of the posts write for qualification like BTech or MTech?
Again, that depends specifically on companies. Companies sometimes they will say, okay, they prefer MTechs. But see, I have in my company people from various backgrounds. I have people who have done BTech. I have people who have done electronics, photonics, etc. Even there is like one very senior guy in my team who has done mechanical engineering. So it's that depends entirely on the company and the requirements. What I understand or what I see is if you can showcase your skills, right? So as I mentioned, you are doing some small sort of you start with smaller circuits and you try to design something which is somewhat useful, like a functional chip design, at least like a part, at least maybe an IP. And if you can showcase it, you can put it in your GitHub page, and you can give that GitHub to the recruiter or whoever is your technical hiring person. Then that will boost your chance. So if they get to know that you know stuff, that you actually have done some stuff, definitely you will have a preference over any other course, any other person, right? So that is definitely there. I would say more than course or anything like that, if you can showcase some practical work, it doesn't have to be like a huge thing, like a entire chip, even like a small functional design, something that you see, something that you can replicate, even that would be good.
Thank you, sir. So,
I mean, what I'm saying is that will boost your chances. It cannot guarantee anything because again, it there are some subjective things also. Certain companies will have their own internal policies where they hire only MTechs for a certain grade. No, that could be some companies' internal policy that we cannot do anything. But there are many companies who will accept people from any background as long as they have the skills. Then again, another aspect is the person who's looking at your resume, shortlisting your resume. If they feel like you know the stuff, they can take you to the next round. Okay, so any other question? Any other questions from anyone else? Yeah, I will share the PPT with the volunteers. You can just share it with the participants. Yeah, anything else? If not, let's wind up. So you can connect with me. Yeah, is there any questions?
Hello.
Yes.
Actually, sir, I am first year TPE student. Doing BTech. What skills should I focus for coming years to get into this field?
Your question was not clear. What you were asking, what courses you were saying, or what topics you should study?
What skills should I focus in coming years?
Okay, skills. Okay, got it.
This field?
Right. Yeah, got it. So you want to know what are the basic skills that you. So first and foremost, I would say is get your electronics basics right. So like your digital electronics, analog electronics. So all about how a transistor works, how the basic elements work, how do you create gates, how do you create digital basic digital elements like adders, multipliers, all those things. So those are like some of the fundamental things which you need to understand. That is the basic. Once you get that right, you can. So if you are interested in digital design, digital VLSI design, you should slowly start exploring any one of the HTL languages like System Verilog or VHDL or something like that. You should start like writing some code and start to play with it and try to understand how it works, how this code gets translated into hardware. And how you can test this code in simulation. So like that, that will be, I would say, the next step. Then analog electronics also, if you are interested in that level of design, you should start going and learn analog basics like op amps or comparators. There are again multiple things, basic building blocks of analog electronics. Then you need to tune. One very important part of analog electronics is you need to tune the various parameters. You need to tune your transistor to work in a certain band, etc. You need to tune your gain, your resistance, etc. There are a lot of concepts there. If you're interested in analog, you can divert in that direction. There are software tools like Spice and all, MATLAB, where you can play with the analog electronics, right? Analog VLSI design also. So once that would be the second step. And the third step I would say is try to do like a small project. Using all this knowledge that you gained, try to do a small project. Uh, if you have professors who are experts in this, try to go with them and try to talk to them and try to do a small project on it, right? Try to do a small project on it. And if you do all these things, if you step by step learn these things, then that will give you a good solid foundation, I would say. I hope it is clear.
Yes, sir. Thank you.
Yeah. Anything else? Okay, so if anybody wants to connect with me, you can connect through this. Usually I am pretty active in LinkedIn, or you can mail me. Yes. If you have any more doubts or something, you can reach out to me. I'd be happy to help when I have time. So sometimes I might not respond, but so just remind me. Right. Once again, I would like to thank the volunteer teams and the organizers and CAS Kerala chapter for inviting me for this event. And I thank all the participants for patiently listening to me in this evening time. I hope it was informative, and I hope that at least some of you would come to the VLSI industry. Yes, thank you all once again, and have a good rest of your day.